Jason Rzucidlo reporting from inside the Disneyland Hotel here in Anaheim for the 2016 SAE Hybrid and Electric Vehicle Technology Symposium. Stay tuned for remarks from Mr. Dean Schlingmann, who's going to be talking about the 2016 Hyundai Sonata Hybrid.
I'll start by giving you a brief background of the Sonata so you all understand why we set the goals and objectives the way we did. I also just realized that I'm the last person standing between you and lunch, so as my time comes to a close, I'll speak faster and faster. So in 2000, in 2011, Hyundai Motor Group, HMG for short, introduced the 6th generation Hyundai Sonata along with the 1st generation hybrid to the North American market. The 1st generation hybrid saw life from 2011 until 2015. Also in 2015, Hyundai Motor Group introduced the 7th generation Sonata to North America and followed that up in 2016 now with the hybrid and the plug-in hybrid variants of the Sonata. So our management got together and defined the design objectives of this next hybrid, which were as follows. First, fuel economy. The Sonata makes up a large segment of the Hyundai Motor America fleet, and as such we needed to develop a powertrain which offers competitive fuel economy, but also helps fulfill HMA's CAFE, CO2, and other regulatory related objectives. Further, the marketplace is becoming increasingly aware of cycle versus off-cycle fuel economy, so our fuel economy targets need to be achievable both in the real world as they are in the laboratory. Second, drivability. We need to provide a segment-leading drive experience to the existing owners, as well as those considering a transition to a hybrid powertrain in their next purchase or lease. Third, cost effectiveness. The gasoline 7th gen Sonata retails in the low 20,000s, so our hybrid architecture must be cost effective such that it is seen as either a break-even or a slight upgrade as compared to its non-hybrid counterparts. At those prices we had to watch our pennies closely and make sure that we were investing in technologies that our customers see the highest system efficiency per dollar spent. All right, and then number 4, collaboration. To achieve all these objectives that I've stated, all HMG departments have to work together. That's both Korean domestic as well as international. So, for example, the interior design team is no longer isolated from the fuel economy team because the materials they use and choose can affect vehicle weight, which is then directly related to fuel economy. So, in short, we're all in this together. All right, so let's start from the outside and work inward. These next couple slides I'm going to kind of fly through. They have more to do with aerodynamic and whatnot, so I'd rather get to the powertrain. That's my area of focus. So in any case, for the hybrid, additional rounding to the front body lines occurred as opposed to the traditional gasoline variant, as well as a reduction in front grille area. Additionally, front grille slats were modified to a more aerodynamic profile, as were the headlights. Sorry. All right, for the rear half of the Sonata Hybrid, body lines are a bit more abrupt. You can see on the gray side. A diffuser was added to the center rear of the bumper, as well as a more pronounced rear spoiler at the top of the trunk lid. And then we added some eco-spoke wheels with optimized open space, which were a little bit more ideal for fuel economy than the traditional Sonata wheel packages. Most notable aero features are shown here with the addition of an active air flap system, a lower air curtain with a frontal aero exhaust ports, and a center floor undercover to help smooth the underside of the vehicle. Lastly, the hybrid package also includes rolling resistance, low rolling resistance tires. All of this resulted in a 0.24 drag coefficient, and we were pretty proud about that. Significant enhancement to the newer 7th Gen Sonata was the increased usage of high-strength steels. As you can see from the chart, we increased high-strength steel usage from 21 to 51%, which helped to reduce base chassis weight as much as possible before we started throwing all of our hybrid hardware and doodads at it. In the case of the 2016 hybrid, we were able to offset enough of our newer additions to maintain our estimated test weight as the previous version at 3750. So now let's get to the nuts and bolts of the Sonata hybrid powertrain architecture, more of what I'm interested in. As you can see from the diagram, we use a TMED system. It's a parallel system. TMED stands for Transmission Mounted Electric Device. This is a very basic system, so just imagine a conventional transverse engine and 6-speed transmission architecture. Remove the torque converter and add a clutch and motor, with the clutch being between the engine and the motor. It's that simple. It's very, very simplistic like that. Some of the benefits we see from this architecture are as follows. First of all, the system's response can be rather fast and easy to control for us when we're changing modes between hybrid and EV modes. This means the engine can be synced with motor speed through a combination of torque demand on the HSG, which is the hybrid starter generator, unit, as well as engine RPM control once the engine is actually started. Switching from HEV to EV mode is as simple as decoupling the two using the clutch, so it's rather simple. Next, shift control and gear-to-gear torque balance now have an increased, or another knob, if you will, that we can turn. We essentially have 0 to 100% torque control within milliseconds. For this hybrid system, we've used a conventional 6-speed automatic transmission. We've actually found that customers are comfortable with a traditional stepped gear feeling, as well as what we feel is a direct feeling the system can provide. In some cases, some of our competitors have a CVT, and this just happens to work better for our cases, and we feel it has a better final drive feel. Finally, the simplicity of the system contributes to its cost effectiveness. The HEV, as well as the plug-in sales volumes, when all is said and done, they're going to be a minority of the Sonata overall sales. But having similar hardware and software between our variants as well as the traditional gasoline allows us to use some common production lines and helps us rein in some of the costs associated with what we're trying to do. All right. Now that I've introduced the TMED system to you, let's take a minute to look at some of its operational modes. So under low speed, light throttle conditions, the powertrain will operate in EV mode, which is shown here. As you can see from the gray box, hopefully folks in the back can see in the gray box, that's the clutch, and that'll be kind of what I'm focused on for the rest of this slide. You can see the clutch is open, so you would only have motive power going to the wheels coming from the motor. All right. When battery state of charge is low or driver demand torque exceeds the motor capabilities, the engine starts, it couples with the motor, and HEV mode is used. So please refer to the clutch, the gray box in this diagram. You can see that the clutch is closed in this case. At the bottom of the page, you'll notice a diagram depicting charge mode. Keep in mind this is only available in the plug-in hybrid version. This is a mode that is used to increase state of charge of the high voltage battery. We added this feature due to customer requests. There are a number of reasons behind the requests. I've heard one example was rather than driving through their local neighborhoods with their kids and family, they'd prefer to charge the battery on the freeway or the highway and use electric mode in their local neighborhoods to reduce local emissions. I'm sure there's plenty more reasons, but we gave customers the option and they can use it however they will. The last mode I'll discuss is depicted on the far right of the slide, and it shows a rarely used operational mode for our system, but it does have some real-world applications. You can see the gray box, the clutch is actually open in this case, and the system is operating in series mode. So the engine is running, it is spinning the HSG, which is then sending electrical power to the motor, through the high voltage battery. Like I said, this is a rarely used operational mode for our system, but imagine yourself getting into your vehicle in an underground parking lot. This is very common in Korea, where a number of our vehicles are sold. You get into the parking garage, into your vehicle, you start driving up floors to get to ground level. You might be traveling along at 1 to 3 kph. You're really kind of crawling along, looking out for people and other vehicles. Anyways, you're probably operating at a vehicle speed which is too slow to couple the engine. You're either going to be below engine idle RPM, or you may end up with some undesirable drivability due to clutch chatter or whatnot. In this mode, you can actually just run the engine, send electrical power to the motor, still provides a nice smooth drivability for the customer to get up to ground level, at which point they'll drive away and I'm sure be an HEV mode or whatever other mode. So, and really this mode doesn't even account for 1% of the drivability or the operational time, but I'm just trying to show it to you to see, so you can see the versatility of the TMED system. It's not quite as black and white as it might appear. Okay, so now we'll dive a little deeper into the powertrain hardware improvements from the first gen to the second gen systems. Something to keep in mind while we're looking at these changes and improvements is that there was not a single change that turned out to be our silver bullet. Unfortunately, it doesn't work that way. No components were off limits, and improvements were typically seen in the 1 to 10% increment. A quick look at this diagram shows our typical front-wheel drive, transverse engine, motor, and transmission location. Most of our hybrid controllers are under the hood, and in the back you can see the high voltage battery. In the case of the plug-in, which I'll show you later, we use a split pack. All right, so first let's start at the heart of the matter with the engine. For the 2016 Sonata Hybrid, we used the 2.0 liter new inline four-cylinder, and when I say new, that's NU. The former first-gen hybrid engine was the 2.4 Theta 2 engine. To this new NU engine, we added a number of technologies not used in our previous hybrid systems. As you can see from the diagram, we changed from multi-port injection to GDI. We understand that there are going to be a number of NVH-related side effects to that GDI decision, but our architecture allows us to stay at a fairly low RPM range during most of our operation, and I say that as compared to some of the CVT architectures and whatnot that are out there. With that in mind, we were able to make some reasonable countermeasures, and we're able to mitigate GDI-related noise pretty well. Next, we added cooled AGR. In addition to fuel economy benefits, we also saw some reduction in CO and NOx generation. Some new low-friction coating technologies were applied to pistons and rings. This next one seems rather obvious, but the new engine incorporates an electric water pump. The previous Theta 2 engine still relied on a mechanical pump, and we saw a number of parasitic losses due to that. Also added to the new engine were a variable pressure oil pump, as well as an engine oil warmer. Both helped to reduce additional parasitic losses. In total, we estimate about a 6.5% efficiency improvement over the Theta 2 system. Further improvements were made to some of our electrical hardware as well. Starting with the traction motor, the winding coil fill factor was improved by about 5% this time around, which helped to improve some of our motor efficiency. In addition to that efficiency improvement, we were able to downsize some of the internal components, and we shed about 4 pounds or 1.8 kilos. The combination of improved efficiency and some software methods, we were able to increase peak power output from 35 kilowatts to 38. For the hybrid starter generator, or HSG, we weren't necessarily looking to increase power or torque on that unit, but we did benefit from some manufacturing advances, which allowed us to shave about 2 pounds off of that component itself. With regards to the transmission system that you see on the right side of the slide, system efficiency was the main focus there. To improve our efficiency, we got away from a 2-pump system. We used to have a mechanical and a low voltage oil pump, and went with a single high voltage oil pump. We also converted from air-cooled to liquid-cooled. The result was about a 9.5% efficiency gain for the transmission system. For our power controls units, we were able to integrate our hybrid control unit, motor control unit, and DC to DC, or LDC, into some of the same control boards. This helped to drop component weight by about 6 pounds. That was actually a pretty big gain for us right there. So to talk more about some of the software improvements we've made, one controls focus which helped to improve efficiency dramatically was our regen braking strategy. And I'm sure everybody looks at regen braking strategy in their own vehicles. As you can see from the charts I've shown here, the red dashed line is our maximum allowable regenerative torque. That's essentially a physical limit of the system. So common sense would say, let's maximize the area underneath the red line and capture as much energy as possible. And the blue line is our actual regenerative torque. We were able to take advantage of the steeper ramp rates through software improvements, which allowed a quicker regeneration per mission and minimized initial brake line pressures when we were not in an emergency situation. And you can see that especially here where the blue line almost overlaps the dotted red line in the new 16 versus 15. Additional logic improvements allowed us to maximize our actual regen torque throughout the maneuver, minimizing residual brake line pressures, which are shown in the light blue line here, versus the old system, which used a lot more hydraulic braking. Essentially, at the end, we were able to improve our regen braking strategy by about 10%. And that's a tough number to quantify, but we're fairly confident in that. All right, for the hybrid battery pack, a few changes took place. We saw a slight increase in battery capacity. We went up to 1.62 kilowatt hours, and this is in the hybrid again, as well as a peak power increase to 56 kilowatt. Battery location was also changed. We went from immediately behind the back seat to underneath the trunk floor. It had a nice side effect that we gained about 10% more space in the trunk area. This is the plug-in. The plug-in battery was large enough that we split it into 2 packs, as I mentioned earlier. One pack remains underneath the trunk floor, while the other is placed immediately behind the rear seat. The split pack configuration ended up it still allowed for ample trunk room. You can still get your golf clubs in the back and whatnot. So we were fairly happy with that. So benefiting from many of the component and controls improvements from the previous system, we were able to improve the syncing strategy for engine startup while transitioning from EV to HEV. Previously, our system saw some engine RPM overshoot while it attempted to sync engine and motor speeds. And you can see that in the first graph over here where the red line crosses over the blue line. Red line is engine RPM, blue line is motor RPM. We were able to, Previously, our system saw some engine RPM overshoot while attempting to sync engine and motor speeds. This was the result of some additional clutch slippage, which was used to help match engine speeds, and it was a little difficult also to control. We did well in the end, but for the new system, not only were we able to minimize our RPM overshoot, but we were able to shorten the syncing time by about 20%, and you can see that in the second graph, where the red line does not overshoot the blue line. And like I mentioned, we were able to shorten sync time by about 20%. In many cases, that actually reduced some of our clutch slippage and helped to add to our system durability. So I mentioned earlier in the presentations, customers are becoming increasingly aware of cycle versus off-cycle fuel economy. So it's important that we give our customers every opportunity to meet or exceed their fuel economy expectations. Seems like at the end of the day, they're always going to want more, and we need to give them more. One of our strategies for doing this is to identify what types of drivers we have behind the wheel. Nobody's going to admit that they're an aggressive driver. I think we probably all have data that shows otherwise. So we've incorporated a driving style detection and analysis software based on a number of driver inputs. I won't bore you with all of their details, but some of them would be average speeds, APS ramp rates, braking habits, and so on. Once we've identified who is behind the wheel, we apply some APS and torque mapping changes to essentially make an aggressive driver's input look like that of a economical driver. We also display a driver score so they can understand what type of driver they really are. You can see that in the black box. That's a shot from the actual IP screen. This can help to not only educate them, but hopefully encourage them to modify their driving habits in the future. So beyond determining driving style, we also incorporated a coasting guide to help customers predict future maneuvers and adjust their driving accordingly. So when a driver has input their destination into the navigation system, we will predict a virtual target speed for either a turn or an upcoming maneuver, and encourage the driver to take their foot off the accelerator pedal and allow the vehicle to coast naturally to their target speed, rather than driving up to the maneuver and then scrubbing speed using too much brake or hydraulic brakes. The driver will receive this coast message via the IP cluster. You can see there is a picture of a foot and the word coast. That starts to blink at them. There's an audible alarm as well that they'll hear that helps them to understand when and what to do. The system relies on destination input in the navigation system, but we have confidence that with enough use, drivers will understand when the system would be telling them to coast into a scenario and essentially adopt the technique over time and hopefully see better rear-wheel fuel economy despite their use of the system or not. To give you a brief idea of what the drive modes look like to the customer, you can see in the picture here that the drive mode buttons are located on the center console area. As a default, we use eco mode in both hybrid and plug-in hybrid, so every key cycle you are in eco mode, we do not latch. Depending on customer preference, both vehicles can also be operated in normal mode. That'll have some slight torque map increases, maybe some changes in shift points and whatnot. Lastly, the hybrid can be operated in sport mode. So that's a hybrid only, not a plug-in, which further increases torque mapping, additional modifications to shift points, and may also modify electric versus hybrid mode operation points. So in sport mode, you would expect to have the engine operating more so. This is what the hybrid mode selection looks like to the customer. These correspond to the modes I discussed earlier in the beginning of my presentation, where you saw operational diagrams for EV, hybrid, and then charge modes. As a default, the powertrain will operate in EV mode until either the SOC is low or until driver demand torque exceeds that of the motor capability. The driver also has the option to sustain battery SOC by pressing the HEV button one time. Additionally, if the customer holds the HEV button for a few seconds, they enter that charge mode that I described earlier.